Thank you. It is an honor to be here. Hi, my name is Woong Shin from Oak Ridge National Laboratory. I am a HPC systems engineer and a researcher in computer systems. Since 2018, I have been working for the Oak Ridge Leadership Computing Facility, OLCF, and one of the focus area was on operational data analytics for the facility's energy efficiency, especially for the Summit supercomputer at OLCF and its central energy plant. So the pursuit for Exascale is almost finished. What's next with energy efficiency? Over a decade, one huge part of the pre-Exascale effort was focused on enabling power and energy efficient systems, just to get there. But at the verge of turning the page into the Exascale era, I have got to think, what's next? What's the next big challenge? Here, I think the keyword is operational complexity, which is a legacy of the current chapter bleeding into the next one. Speaking up front, I think this may be the next thing we'd be fighting with. So what's the impact of this complexity in energy efficiency? And how do we tame it moving forward? Today, I will expand this topic based on the findings and lessons I have learned by supporting Summit with its operational data. Summit is the US Department of Energy's 200 petaflops pre-exascale supercomputer. Due to its power density, Summit uses direct liquid cooling to remove heat from its CPUs and GPUs. Also, to achieve energy efficiency, the system is cooled using medium temperature water, which is about 70 degrees Fahrenheit in supply. This makes it possible to use water-side economizers for 80% of the time of the year instead of chiller water, giving us annualized PUE of 1.1. To support this system in operations, I have worked on heavily instrumenting this system to fulfill the monitoring and analysis needs. In doing so, we've been employing some extreme practices. Even with a single use case, we have pursued to collect from an extreme scope to get a holistic view of the data center. We collect data from the facility and the compute system, along with the job scheduler allocation data, reliability data, and regional weather data. This has been done in extreme granularity and resolution. Especially for the compute, we capture node and component level power and thermal data that covers many things in the node at a rather higher resolution of 1 Hertz. This was around 100 metrics per node, streaming 460K metrics per second. And finally, we have made an extreme decision to preserve all of this raw data for further research and development. These practices were all possible with reasonable impact and resources due to many things. I cannot go too much into detail, but to name a few, I can list a few things. To enable no impact in high-resolution data, especially from the compute, we leveraged push-based out-of-band telemetry streams from the BMCs. To enable data from the facility, we have established a use case of SCADA to HPC network gateway data channel, which in itself was a challenge. And finally, we have leveraged advances in open source big data tools that enhanced our capability to store and handle large quantities of data. With such practices in place, we have built a near real-time monitoring system that provides a holistic view of the HPC data center at an instant. With the high-resolution data, we have explored potential optimization, especially in the facility set points, really following the rather dynamic HPC load. This eventually was not achieved, but the effort in itself revealed a lot of things about HPC energy efficiency, which led to many of the points I'm making in this talk. Finally, with the archived data, we were able to do a full-scale, full-coverage analysis of the data set to reveal the nature of a pre-exascale supercomputer. So what did we learn? Number 1, energy-efficient HPC is an end-to-end deal. Performance, energy, reliability all go hand in hand. In our case, the medium temperature water cooling control was a PUE enhancement business, but still we had to look into the compute system because of reliability, which I think the ramifications are profound. For us, component level conservatism had to be challenged to achieve better PUE, but it had to be carried out without harming the system. Interestingly, this required the facility side engineer to monitor CPU and GPU level temperature and alerts. Everything here is a tuning and balancing act, but finding the balance requires tools and frameworks and data with the right scope and etc. And it also requires planning and effort. End of the day, finding the balance gets to be done by the site, and it is a site-specific thing. Performance tuning is usually done here, but how about end-to-end cooling system tuning for things like PUE? Our initial effort was done using HPL, and it was done in a 1-rack setting by gradually cutting the water flow to see how far we can go. But looking back, I think we could have done things differently with early deployment of the monitoring system, more sensor data, better tools, and different benchmarks to understand the characteristics of the node and the interaction with the facility. Number 2, we need to look into the workload dynamics of HPC applications. Speaking of a balancing act, what it is to achieve the global optimum in the face of so many knobs we have in front of us. What does it take to get there? When such tuning effort goes to an extreme, this may no longer be a static one. Optimal settings may change as external conditions such as weather and workloads change because of the way how these systems are built. If absolutely required, there are some savings opportunities by making the data center's energy consumption proportional to the load, even for the facility. This might be possible with cloud data centers, but it turns out for HPC, this may not quite be possible. Based on a full year data analysis using the high-resolution data, it revealed that violent large swings of 4 megawatts to 7 megawatts can happen within a few tens of seconds. In this case, following the workload dynamics meant potentially going beyond the speed of what the control system could safely respond to. Engineering the solutions for this phenomenon requires quantified information of this behavior, but surprisingly, this information was extremely difficult to get. This leads to my third point. Number 3, we have lots of data, but we may not have the right data because we do not have the end-to-end understanding of these advanced use cases. Data is key in addressing the operational complexity. I think there's no question for that. So we all do collect a lot of data. But unfortunately, we may lack the right data we really need to attack a particular problem, if the collection operation is not driven by use case. Turns out, even within a single stream, not all features are operationally important depending on the context. In the example of following the HPC load, one possible solution may be predicting the power swing behavior by modeling the data. We tried that by training a neural network, RNN. We could achieve high accuracy for the whole period, but found that the result was completely misleading. The accuracy of the swings that we really care about themselves were actually useless because the model wasn't able to experience the swings too much, despite having the full year of the data. Such an experience led us to think that use case development is key in being effective in data collection. This actually requires a community-level effort, which brings to my fourth point. Use cases of advanced data analytics need investments, both in exploration and implementation. And, thinking about the usage of data is exciting, but the thing is, still, this is an area that requires research and development. The advanced data usage in the age of big data, data science, AI, and machine learning has not been matured in this particular community to a level which we use products like Siri and Alexa. Not all sites need to do this, and we do not absolutely have to do this, but when pursuing, one has to realize that such exploration requires a certain degree of investments, and depending on the expectations, the cost can be huge and may not fit into the budget in hand. I think this is where the community can collaborate to share results, case studies, and best practices. What if we can find ways to share the burden and reduce the cost of such development and adaptations? So far, I think, again, operational complexity will be the legacy of this chapter of history. There are just too many knobs we need to turn to make these things efficient. Energy efficient HPC in the next chapter may mean taming this complexity in new ways. In the era of complexity, reaching a global optimum would require new mindsets and investment in tools, frameworks, methods, data, and explorations end to end. And this might be the way we achieve energy efficiency. Thank you for listening.